Today we're going to take a look at esters. The general formula of an ester will allow us to understand them a little greater. As we can see here, this is our carbonyl group, composed of a carbon atom double bonded to an oxygen atom. This carbonyl group is further bonded to a single oxygen atom. And this is what defines an ester. To name an ester, we will be following these 4 steps. Here we have the components of an ester: ethanol and butanoic acid. To start with, we take the alcohol, ethanol in this case. To properly name an ester, we take off the -anol ending, and we add a -yl ending. Now, if you remember, the second component of our ester was butanoic acid. We eliminate the acid part, because of course we are making an ester, and we also eliminate the oic ending. And we add an O8 ending. So, if everything goes according to plan, ethanol plus butanoic acid when formed as an ester will make ethyl butanoate. This process is called esterification. For an esterification to occur, we must generally need an acidic catalyst, such as H2SO4 and/or a little bit of heat. I know that an ester is a polar molecule, or somewhat polar. I know this because of the carbonyl group bonded to the oxygen. Oxygen has a higher electronegativity of 3.44. Carbon has an electronegativity of 2.55. What this confers is that there is a slight dipole-dipole bond between the C and the O, with there being a slightly negative charge on the O and a slightly positive charge on the C. In polarity. What this also means is that it is polar. This means it has slight solubility in water. As we can see here, esters are slightly less soluble in water compared to their parent makeup. As we see here, the acid, which is characterized by an OH group, has stronger dipole-dipole forces than that of the ester. This means that the acid is more soluble in water than the ester. And so, in comparison, esters are slightly less polar and therefore less soluble in water, compared to their parent acids, which contain the hydroxide group. This makes them more soluble in water. Next, we will move on to melting and boiling points. The ester stacks up quite the same to their parent acids, just like it did in the solubility test. Because of the ester's less powerful dipole-dipole forces, this makes their melting points lower. Their parent acids have higher melting points because of their stronger dipole-dipole forces. When comparing just esters, we must take into account London forces. Smaller esters have less components and therefore lower London forces. This makes their melting and boiling points lower because they have less molecules. Longer esters will have higher melting and boiling points because they have more components, which makes their London forces stronger, or dispersion forces if you wish. Here we have an example of an esterification. We have our two components of an ester, an acid and an alcohol. When an esterification process occurs, we end up with the ester, with the general formula and also, as we can see, we have the OH group from the acid. Now, we know from the previous clip that we lose this OH group. And as we can see here on the alcohol, we also lose this hydrogen. Now, they don't just take off and leave. What this makes is water, or HOH if you prefer. This process is called esterification. Here we have ethanoic acid, and here we have ethanol. When an acidic catalyst is used, such as sulfuric acid, H2SO4, the esterification process will occur. What we get from this reaction is the ester known as ethyl ethanoate. It has a chemical formula which looks like this. Notice that we have water left over. A reversal of esterification is called saponification. And this is a reaction which uses an ester. It is in essence a hydrolysis reaction. As we can see here, this is the framework of saponification. When an ester is acted upon by a strong base, such as NaOH, we end up with the sodium salt of the acid plus the alcohol. This sodium salt is a precipitate, and it is what we know as soap, hence saponification. Thank you for watching, and I hope you learned a little more about esters today.